All right. So last time we were talking about alcohols. We said due to alcohols hydrogen bonding, they have significantly higher boiling points than other molecules of similar mass due to their hydrogen bonding. If there aren't too many carbons, like a 1, 2, or 3 carbon chain, the alcohol should be readily soluble in water. So the next section is we're going to talk about acidity of alcohols. And this is especially relevant if you have an alcohol and you want to convert it into a strong base / strong nucleophile. So an alcohol is acidic because this proton here, if it were picked off by a base, would leave behind a relatively stable negative charge. So what does that mean? It's really kind of unstable, especially if there's no resonance or induction to stabilize that negative. But because oxygen is such an electronegative atom, it attracts electrons so strongly, it's got a fair number of protons in its nucleus, it can hold that negative charge in. Would it be more or less stable if it were a sulfur? Well, hopefully you remember from OChem 1 that the larger the atom, usually the more stable it is with the negative charge. So because sulfur has a lot more protons in its nucleus, 16 protons, that extra electron would give it the equivalent of 17 total electrons. So the ratio there is pretty close to a 1-to-1 ratio. For oxygen, though, with only 8 protons, the extra 9th electron creates a ratio that's a little bit more deviating from a 1-to-1 ratio. So the charge, even though they both carry the same net charge, one is a bit more charge imbalanced. So as far as atoms holding a negative, oxygen's kind of in the middle. It's not the most stable. It's not the least stable. So as long as I start with an atom that's even less stable with the negative, I have the potential ability to pick off this proton and create a negative charge on what was the alcohol. So hydride's a great choice for that. One group did this similar reaction last semester, and they saw that sodium hydride is a solid. What's nice about that is its reaction is quite product favored, and when it picks up a proton, it shifts to the product side, so we can see that solid disappearing, giving us evidence that this reaction is occurring, and it produces hydrogen gas. You can see that bubbling out during the reaction. But what's going on with the hydride here is hydrogen has 1 proton, and giving it 2 electrons means there's twice as much negative compared to the positive. So it still has only a net -1, but the ratio is very much deviating from a 1-to-1 ratio. So that means that's going to be especially unstable. So we'd have to buy this from a chemical company or something if we wanted a negative charge on hydrogen, add those two together, and we could convert the ethanol into the ethoxide, which could be a great nucleophile or a great base, depending on what you're reacting it with. Another option to deprotonate an alcohol is to use sodium, potassium, or lithium metal. Sodium is probably the most common. The other two are harder to get your hands on. So what would happen in this reaction is the sodium, if it's neutral and with no charge zone, we recognize it as 1 valence electron, right? It's in group 1A. And to make its noble gas configuration, it needs to lose that electron. So when it reacts with the alcohol, it needs to give up that electron, but there's really nowhere here that can accept another electron. All these atoms already have complete noble gas configurations. So what's going to happen here is this OH bond is going to break. The oxygen is going to take 1 electron, and that's going to join up with the electron from the sodium to make the alkoxide. The sodium becomes positive. now that it makes a noble gas configuration. It doesn't have that electron anymore. The other electron from the bond is going to go to the hydrogen. So that makes a hydrogen radical, which is pretty unstable because it doesn't have a noble gas configuration. So what will happen again is another set of these molecules will do the same thing. So once this happens twice, and I get two of these, and two of these, and two of these, the two hydrogens will couple or terminate with one another to make hydrogen gas. So that reaction also bubbles out hydrogen gas as it's occurring. And it produces the alkoxide, which is the point. Even though this is not a proton transfer reaction, it's not really an acid-base reaction, it's a free radical type mechanism, it gives the same resulting products as the reaction we just saw up here. So make sure you're available or familiar with both of those. So we want to put alcohols in the context of other molecules in terms of how acidic they are. So you want to remember that the lower the pKa value, the more acidic something is. So if it's a lower pKa, especially if it's a negative pKa, that's a very strong acid. So we're talking about HCl, HBr, HI, sulfuric acid, nitric acid. Those will so readily take the electron away from the proton that they effectively react 100% in water. Every molecule will force a proton onto water to make H3O+. Alcohols are not nearly as acidic, so they're not strong acids, they're weak acids. They're quite weak, and most of them have pKa's high enough that the reactivity in water is minimal, and in most cases negligible. So let's take a quick look at that right here. We'll come back. So water's pKa is about 15.7. So we'll just look at a random alcohol. It's got a pKa of 18. So if the water were to pick up that proton and these electrons were to stay behind, that would produce H3O+ and the alkoxide, oops, ignore those shouldn't be there, and the alkoxide. So the acid on this side is the cyclohexanol, its pKa is 18. This could act as an acid because it has a pKa value, but in this case it's acting as a base. If it's the molecule picking up a proton, it's acting as a base to create H3O+. So of the two products, the acid is the H3O+, and its pKa is around 0 to 1. So if I have a pKa of 18 on one side of my equilibrium and a pKa of 1 on the other side, from what we learned last semester, we know the equilibrium is going to shift dramatically toward the side with the higher pKa. And the more there is a difference between those pKa's, the more the equilibrium will shift in that direction. So 18 minus 1 gives me the difference between the two pKa values, 17, which means when this reaches equilibrium, there's going to be 10 to the 17th more reactants than products. And so again, that's a reaction that basically doesn't produce products. So when alcohols are just sitting in water, they don't really act as acids or bases. The extent to which they would react would be very minimal when it reaches equilibrium, almost nothing compared to, or a negligible trace amount compared to what we're starting with. So in the context of, is something an acid, normally we ask the question, is it acidic enough that will force a proton onto water? And alcohols aren't really acidic enough to force a proton onto water. They are more acidic than alkanes and amines. because these have even higher pKa's, and they don't react in water really to any significant degree. So we want to be able to be at least familiar with these rough pKa ranges so that we can say when we have a compound whether it's likely to react, and if so, to what extent. So let's take a look at the pKa's of these two. So we see a significant difference. What's the difference in structure? Here I have an aromatic ring. Here I don't. Here I've got alternating pi bonds around the ring that can engage in resonance. Here I don't. Right? So if this one is to react with water, the pKa is much higher. It's a very weak acid. It's not likely to donate the proton because when it does, the resulting negative charge can't be stabilized effectively in any really major way. So I should have mentioned that over here just to point out, if you recall from last semester, this acronym that we actually modified, when we modified the acronym, we said we can use aereo or scario or carios. It doesn't really matter too much. The solvation part is a little bit tricky. It could be a really major factor or it could be a really minor factor, so you could really put it on the beginning or the end. It depends on the situation. But the idea here is if you have an acid or a base, you can predict how strong or weak it is based on the letters in this acronym by analyzing one by one. When the molecule reacts, if it has a charge or forms a charge, how stable is the charge based on these acronyms? And so that's what we're going to go through one by one. So the first one is the atom that's carrying the charge. So this is specifically for charged atoms. So in this case, if this carbon, our group represents a carbon, were to give up a proton, it would produce a negatively charged carbon. If the nitrogen were to give up a proton and keep a pair of electrons, it would produce a negatively charged nitrogen. If the alcohol were to do that, it would produce an alkoxide, a negatively charged oxygen. And if this were a halogen, like a chlorine, bromine, iodine, obviously it would produce a negatively charged halide. So the atom holding that charge, whether it's carbon, nitrogen, oxygen, chlorine, the size of the atom and the number of protons in its nucleus determines how stable that negative charge is on that atom. Right? So we said the larger the atom, the more stable it is with the negative, the more likely that molecule is to be an acid to produce that negative, giving up the proton. If it's a smaller atom but it has more protons than another one that's similar in size, the extra proton pulls the electrons closer, stabilizing the negative. It also creates slightly less of a dramatically lopsided charge ratio. So the charge ratio is not quite as imbalanced. So that's a little bit more stable. So it's more likely to give up the proton, slightly stronger acid than other situations. So nitrogen and carbon have less protons, creates more of a charge imbalance when they exist with the negative. So they're very unlikely to do that. And that means that they'll be very unlikely to give up a proton, which makes them very weak acids, and those pKa values reflect that. So the next letter in the acronym is R for resonance. And so that's what this example here is meant to demonstrate. I got a little ahead of myself there. So when there's no resonance to stabilize the negative versus when there is, we see a significant difference in the pKa. So we're not looking at the stability of the neutral molecule. The neutral molecules are both equally stable, and neither of them is really unstable. But once they donate a proton to create a negative, we can judge by how stable or unstable that negative is, how likely that original molecule was to give up the proton. So in this case, this is a stronger acid. I know that because its pKa is 8 pKa units lower. That means it's 10 to the 8th or 100 million times stronger as an acid than the other molecule. And the reason for that is because it can stabilize a negative charge that results. It's much more likely to give up a proton and hold the electrons behind if those new electrons don't create a really unstable situation. Because if they do and there's no way to stabilize it, well, then it would just grab the proton back and go back to the original side, meaning that the original acid wasn't as strong and wasn't as likely to donate a proton if it's just going to be picking it back up when it reaches equilibrium. Most of the molecules will exist in the form of the reactant. So just to point out the resonance here, in case you don't see it, these electrons can swing in and move out to this carbon. That will create a negative on the carbon. Then they could move in here and push these out onto that carbon. To create a negative on that carbon, or they could shift in and move on to this carbon. Oops, I'm going to put that there. I'll just draw it here instead. Negative here, here, and here. And then those could shift back in, back up to the oxygen, get back to the original structure. So there are 4 resonance contributors, and the negative charge is shared instantaneously over the oxygen in 3 different carbons. So each of those atoms will only really carry a partial or fraction of a negative charge, which isn't nearly as unstable as a full localized charge that can't be spread out at all through resonance. So it's a big difference in what the resonance does for the structure. So that's why resonance is at near the beginning of the acronym. It's not as big of a pKa difference as it would be if we had a different element stabilizing the negative. That makes a much bigger difference. But since these are both oxygens to stabilize the negative charge, the extra resonance stabilizes it by 8 pKa units roughly, which is a fair amount, and that creates a big difference in how acidic one is versus the other. Specifically, it means that NaOH is not strong enough of a base to deprotonate the cyclohexanol, but it is strong enough to deprotonate the phenol. Right? So let's take a look at that. So if I add OH minus from NaOH, the negative charge, pick up this proton, electrons would stay behind there. That would produce the conjugate base of the cyclohexanol and water. So in this equilibrium, the acid on one side has a pKa of 18. The acid on the other side, which is a water, because it could donate a proton back to the oxygen, has a pKa, let's just round that up to 16. So the equilibrium should favor the side, at least somewhat, with a higher pKa. The pKa difference is only 2, so that's 10 to the second reactants for every 1 product. So it's only 100 times more reactants than products, but still, that's almost exclusively reactants. So if I want to make this oxygen negative, and then I want that to happen for most of the molecules so that that can happen to most of the molecules and then react further from there, this base is not going to be strong enough. I need a base that will produce a higher pKa when it picks up a proton to shift that equilibrium toward the products if I want to make the products. In the case of the phenol, though, if I add OH minus by adding NaOH or KOH, and it picks off a proton, because of the resonance we just saw, the negative charge on this oxygen is stabilized by resonance, which means it's going to be shifting the equilibrium a lot more toward the product side. And we can see that mathematically if we look at the pKa. It's the pKa of water, is about 16. So that's 6 pKa units higher than phenol, which means it's going to favor the product side by about 10 to the 6th. Or in other words, for every one of these structures, there's 10 to the 6th or a million of these once it reaches equilibrium. So in effect, I can completely convert, for all intents and purposes, all of this phenol molecule into the base if I want to then use that base to act as a nucleophile or further in some other reaction. So make sure you understand how to use the pKa values to predict which side of the equilibrium is going to be favored and whether or not a substance is going to be strong enough to react. A base is going to be strong enough to pick up a proton from a specific type of alcohol. All right, so in the acronym, we talked about the atom carrying the charge, whether there's resonance to stabilize the charge. We also want to consider induction. So induction has to do with electronegativity differences and shifting of sigma bonds toward more electronegative atoms, right? So if I have chlorine, that's more electronegative than carbon. So chlorine will attract electrons away from carbon. That creates a pretty large partial positive there. That normally we think of carbon, and carbon is having the same electronegativity. But if one has a bit of a positive due to its electrons being shifted away from its nucleus, that positive and that nucleus will attract the shared electrons there a little bit. And that will extend that positive a little bit farther. So I don't have that happening over here much. So if the ethanol acts as an acid and donates a proton to produce ethoxide, there's really nothing to attract to this negative or stabilize it. But if the same thing happens here, and these electrons stay behind as the proton's picked off by some base, what I now effectively have is a situation where the negative charge that results on the oxygen is right next to this partial positive. It's small, but it's enough to attract some of the shared electrons away from the oxygen. And that stabilizes. The problem with this oxygen is there's too many electrons. It's too negative. The negative is all concentrated in one space. So we're not affecting the lone pairs like we would in resonance. We're affecting the sigma bond. In induction, sigma bonds shift due to some kind of charge attraction or repulsion. But in this case, the negative charges of the sigma bond would just be shifted a little more toward the carbon than normal, and that takes a little negative away from the oxygen. So it's not really a full negative one. It's going to be just slightly less. It's going to be a large partial negative. So it's still going to be pretty unstable, but not as much. And we can see the difference in pKa that makes. Having those 3 chlorines in there affects it by about 4 pKa units. So this is about 10,000 times stronger as an acid than the one that doesn't have the induction. So induction is a significant factor that can affect how strong of an acid an alcohol will be. The next factor is the orbital that's holding the charge. And in this case, for an oxygen, that's pretty much always going to be an sp3. Unless there's resonance to stabilize it, in which case the resonance would be what would be stabilizing that. If there's no resonance and I'm looking at the orbital, it's pretty much always going to be an sp3. So that means that this factor, it won't allow us to distinguish between one alcohol and another. So that means we used this factor last semester to distinguish between some carbons. We said if a carbon has a negative and it holds its lone pair in an sp3 orbital that's more, or an sp orbital that's more compact versus an sp3 that's more elongated, then the negative charge in the more compact orbital is going to be more stable because it's going to be closer to the nucleus, forming a stronger attraction. But for oxygen, the negative charges are pretty much always in sp3 orbitals, and if they're not, it would only be due to resonance, and so it would be resonance that would be stabilizing them more so than the orbital. And that's why resonance comes before orbital in the ordering of the letters of the acronym. So as far as alcohols go, this is not really going to be a factor that is going to determine much. So that gets through the main letters of the acronym that the book focuses on, but we also talked about solvation. For some reason they talk about that as a factor, but they don't include it in the acronym. I don't know why. I'm going to include it. We also talked about the quantity of charge. They don't include that in the acronym, although they do talk about it. So C here stands for charge, or quantity of charge. And the solvation is what the S stands for. So solvation can be a factor. If I've got 2 alcohols in the same solvent, it may not be much of a factor. But we can see here it is a factor, although it's a minimal factor because it doesn't create much of a difference in the pKa. So what's happening here with the solvation? Well, we want to keep in mind that same general idea. if this molecule is a stronger acid, which it is, because it has slightly lower pKa than the other one, that must mean that it will more readily donate a proton, keep the shared electrons behind, and stabilize the negative charge that results. So somehow this negative is more stable than the one that would result when these electrons stay behind on that structure there, on the terbutanol. So why is this more stable? Well, it's the same quantity of charge. They both have a -1. It's the same atom carrying the charge. They're both on oxygen. Neither can spread out that charge through multiple atoms through resonance because there's no neighboring p orbitals to overlap. So the lone pairs here are going to be in sp3 orbitals rather than p orbitals. There's no induction. There's no electronegative atoms to help create partial positives around here that would help to attract and stabilize the charge by spreading it out. And the orbital holding the charge in both cases is in sp3, so there's no difference. So the solvation is the only factor that we can look to. So we want to explain that. So solvation occurs when the solvent molecules that surround the structure form attractions to it. So we want to look at what the solvent is going to do, right? So here is my ethoxide. Here's my negatively charged oxygen. That's why it's red in this area. So whatever the solvent is, whether it's polar and has a permanent dipole, or whether it's nonpolar, it will only shift electrons randomly or in response to this charge. Either way, it can at least temporarily create a negative side and a positive side. If it's a polar solvent, it would permanently have opposite charges on opposite ends due to electronegativity differences. That creates a situation where the solvent molecules come in and form attractions to the charge. So solvation, I put the letter S at the beginning of this acronym. You can put it at the end or at the beginning, but I like it at the beginning because it helps me remember that if there were no solvent at all, this would be really unstable with a negative. So the role of the solvent might not be that different from one molecule to the next, but if we were to look at the situation where we're comparing a solvated charge with partial charges from the solvent nearby versus an unsolvated charge, something that forms like in the gas phase where there's no way anything can come in and form attractions, the pKa of this acid that would produce the solvated charge would be tens of units lower than the pKa of the unsolvated charge. So we're looking at potentially dozens of pKa units. It's a massive difference in how stable a negative is. It's stabilized through solvation versus no solvation at all. But if we're looking at water and we're comparing ethoxide and terbutoxide in terms of see which is more stable, then sterics often is at play, right? So the ethyl group here isn't very big, and so it doesn't block out, and I can get multiple solvent molecules to form multiple attractions to help stabilize it. But the terbutyl group is a bigger group, so I can maybe only get 2 or 3 solvent molecules to bring in partial charges, form attractions, and stabilize it. So when it comes to solvation, that goes hand in hand with sterics. It goes hand in hand with whether or not there is a solvent. If there's a solvent, it's definitely going to stabilize it more than no solvent at all. It goes hand in hand with whether or not the solvent is polar. If it's a dipole and it's got large partial charges, it's going to stabilize it better than maybe something that's non-polar and only forms temporary minor partial charges to help stabilize it. But even if two structures are in the same solvent and they can form the same strength of attraction, if there's sterics that blocks out a certain number of those solvent molecules so they can't get as many in there, it's not going to stabilize it as much as it would otherwise. And that's the difference in this particular example. That's the reason why we see this specific 2-unit difference in the pKa values, specifically because the sterics of the terbutyl group makes this less stable when it donates a proton because you can't get as many solvent molecules in to attract to it, so its pKa is a couple units higher. All right, so let's apply this concept to a couple examples. Look at this one, then we'll look at the first quiz question. So here, what's going on? Well, in each one of these cases, I have an H that's going to be donated. Right, so if we're looking at ranking the pKa's of these, we want to look at how readily will these donate a proton. And so I want to go through the acronym. I probably want to save solvation till the end, even though it's at the beginning, to illustrate how important it can be if there were no solvent at all. But generally, unless it says otherwise, we would assume that they're all in the same solvent, in which case it probably only makes a minor difference, like we noticed it making a minor difference between these pKa's when the sterics was blocking the solvent to some extent. So if they're in the same solvent, or if it doesn't say, you can assume they're in the same solvent. That's not going to be the biggest factor. So the biggest factor is going to be the quantity of charge. So since these are all neutral, but this one has a positive, that one, we want to look at how much charge is there going to be if it donates a proton. So normally I would maybe try to donate a proton from this nitrogen to balance the charge, but it doesn't have a proton. It's only bonded to carbons. So this is the most likely proton to be donated. So if I donate that, what do I get? I got a nitrogen here with a positive, and I got an O with a negative. So I might think that the oxygen's carrying a negative charge, but I have to understand as soon as that forms, there's going to be a resonance. This can shift in here and push a pair of electrons onto the nitrogen. So when that occurs, I'm going to create a CO double bond right in there. The nitrogen now has a lone pair from this pi electrons that shifted onto it. And that means there's no charge at all in my structure in the major resonance contributor. So this is a minor but significant contributor, but it's very minor because the formal charges make it a lot less stable. So on average, the oxygen and nitrogen carry almost no charge. And really, they don't carry any formal charge because it's the major contributor. So if a structure can donate a proton and be stable with no charge, it's going to be pretty likely to donate that proton. So that's going to be a low pKa value. It's going to be very low because it's going to be very easy to donate a proton if upon doing so, it doesn't create an unstable structure. It creates a structure that can readily exist. So let's look at these other ones. If these other ones donate a proton, they will produce a negative charge on an oxygen. This one has a CO double bond nearby. This one does not. And this one has some carbon groups that are basically creating resonance and blocking things. So when this one donates a proton, I just have a negative charge on an oxygen. When this one donates a proton, there's a negative charge on that oxygen, but there's these ethyl groups nearby. So in terms of these three, call these A, B, C, D. So B definitely has the lowest pKa because it's the only one that doesn't produce a charge upon losing a proton. The other ones produce these unstable negative charges upon donating a proton, so they're not as likely to donate it. Or in other words, they're more likely to don't pick the proton back up and go back to the original, which means they're not very strong acids and they don't have very low pKa's. But we want to distinguish between them. So since in each one of these it's the same atom carrying the negative charge, that's not going to be a factor. Are any of these stabilized by resonance? These three that we're still looking to distinguish between, not really. So it kind of looks like a carboxylic acid here, but it's too far away. I can't shift these electrons in because this carbon right here is sp3 hybridized. So there's no p orbital to overlap with the p orbital on the oxygen to allow for resonance. So there wouldn't be any resonance in any one of these three. So then I would look for induction. And that's what I see here. This oxygen, the CO double bond, there's a big electronegativity difference there. So electrons are going to shift up and create a nice large partial positive there. That's going to attract these electrons, create a partial positive there. And that's going to help to attract electrons away from this oxygen. So this oxygen is not going to have as much electron density around it as this oxygen down here would, which means it's not going to be as unstable. So if we're ranking the pKa's, pKa highest versus lowest, we put B as the lowest pKa, then A. And then looking between C and D, it's the same atom carrying the charge. Neither has resonance to stabilize the charge. Neither has induction. They both have their lone pairs in sp3 orbitals, so none of that makes a difference. The only thing that matters there would be the sterics and solvation. So here with these ethyl groups, it's going to be harder for whatever the solvent molecules are, likely water, to bring in partial positives and attract, because the sterics of those ethyl groups are going to block them out. So here the oxygens is kind of out in space though, so you might be able to get a lot more solvent molecules around there, each one bringing in its partial positive side to attract to that negative. That's really going to help to stabilize it. Not probably as much as induction, assuming they're both in the same solvent, because the solvation can also stabilize this negative. So that stabilization, in addition to the induction stabilization, would stabilize the conjugate base of acid A more, and that's why acid A has a lower pKa. But then I could say C, and then D would be the highest because it's less likely to give up a proton if it produces an unstable negative that can't be effectively stabilized through any of these things, including solvation due to sterics. Hope that makes sense. If you have any questions about that, let me know. So here was the example from today's quiz, the first quiz question. So what we're looking at here is ranking these, so we can go from lowest pKa to highest pKa. So what I'm noticing here is that the charge, the quantity of charge, is going to be the same on each one of these. Each one of these is going to have to lose a proton and create a negative, and that's what we're judging. How easy is it for one to lose a proton and create a negative versus the others? That's how we're going to rank them. If they're neutral to begin with, we can't just rank their structures. We only can use this acronym to help us rank the stability of charged structures. So if they're not charged, we have to imagine them losing a proton to say which one will stabilize the resulting charge more. The more stabilized the charge is, the results after losing a proton, the more likely it will be to lose a proton, the lower its pKa will be. So what are we seeing here? Okay, well in this one I see well it's the same atom holding the charge, oxygen in each case, so that's not going to help me distinguish. They each have the same quantity of charge, so that's not going to help me distinguish. So I look for resonance, and I see that here. Any one of these three lone pairs could exist in a p orbital, could shift in here and move these electrons to that carbon. That would spread the negative to a carbon. So the negative is more stable in the oxygen than carbon, but spreading out over multiple atoms, putting only a partial charge on each is more stable even so. So shifting that in and moving out here would create another contributor. Pretty unstable as a contributor, but none of these contributors exist. What exists is the hybrid or average. So if we're to look at what that hybrid would look like, there would only be a partial negative at each one of these sites. There'd be a bigger partial negative on the oxygen than on the carbons, but no single atom would have to carry a full charge imbalance. So it'd be much more stable. So this is going to be the lowest pKa because it produces the most stable conjugate base. After that, D would be next because of these chlorines, as we showed in the earlier example. The chlorines create partial positives, and that helps to attract electrons and shift them away from the oxygen. So the oxygen, when it creates a negative, is not going to be quite a full negative. Induction will not spread out the charge as effectively as resonance, because in resonance the charge is instantaneously spread out due to electrons immediately shifting around in a large molecular orbital extending over all these atoms. In induction, it's just a sigma bond that ever so slightly shifts away due to its attraction to the neighboring atom. So just a slight shift just means there's going to be a slightly less than a full -1 on that oxygen. And so that's going to be a little bit stabilized, but not as much as C. So that's going to have a lower pKa than B and A, because in B and A, the negative charge is really only on one atom. That's a concentrated negative in one spot. That's pretty unstable. If it's on a primary carbon and lots of solvent molecules can surround it and help stabilize it, it's going to be more stable than if it's on a tertiary carbon where these methyl groups are blocking some solvation. So the more solvation, the more stabilized it is, because there's more partial positives that can be brought in by all the solvent molecules. And the more stable that is, the more likely it was to give up the proton to form the relatively stabilized charge. So the lower the pKa. And so that would be the ranking. So I'll definitely look at your quiz questions here after the lecture and give you feedback on that. All right, so that's the section about alcohols from an acid-base perspective. So be ready for questions about that on next week's exams. So the next thing we're going to talk about is how to make an alcohol. So if your goal is to produce an alcohol, a molecule with an OH functional group on a carbon, there's a couple ways we can do that. We learned some last semester. We talked about some substitution reactions. So if I have X as a leaving group, could be a chloride or a bromide or some other great leaving group. There's two ways I can convert that into alcohol. We said if we have a primary carbon, then we would expect an SN2, and we could use NaOH or KOH. The OH minus is a good nucleophile. It can come in here, push out the leaving group, and give an alcohol. So that's a good way to make a primary alcohol. It won't work very easily if I have too much sterics, though, because the SN2 requires the OH to come in at the same time that the leaving group is leaving. And that won't happen if it's too crowded. If it's tertiary, then we can do an SN1. Right, so if the leaving group's on a tertiary carbon, it's too crowded for any nucleophile to come in and push the leaving group out. So we definitely cannot do an SN2. So we're going to see an SN1 where the leaving group will leave first. So this is a review from last semester, creating a carbocation. And now that the leaving group's gone and it's flat, I should have drawn it more flat, the nucleophile can come in from any side. I can't use a strong nucleophile like we did in an SN2, though. I need a weak nucleophile, like water. The water can then come in and attack the carbocation. And then it still needs to be deprotonated. So another water would pick up a proton and make the alcohol. So that would be how we make a tertiary alcohol. Why can't we use a strong base there? Oh, I gave away the answer. I meant to say, why can't we use a strong nucleophile like OH minus? Well, the reason is because it would act like a base. If we use a strong nucleophile, it wouldn't wait for the carbocation to form and then attack. See a lot of students doing that. Just because you want it to happen doesn't mean it'll happen. So you can't expect a leaving group to leave and then a strong nucleophile to come in, because a strong nucleophile usually would get involved right away. If it's a nucleophile only and it can't act as a base, then it could wait and come in on the carbocation. But if it's also a strong base like OH minus or methoxide or ethoxide or terpbutoxide, it would pick off one of these beta hydrogens, which would shift electrons in and push out the leaving group. That would be an elimination reaction. So there's a competing elimination reaction when my nucleophile is also a base. And the more crowded the site is where the leaving group is, the more likely I am to get elimination, which would result in alkene, obviously, rather than the substitution I want if I'm trying to make an alcohol. So these are the methods we talked about for making alcohols last semester through substitution specifically. So here are those two examples worked out. Why can't I use a stronger nucleophile like OH minus in an SN1? Because the OH minus would end up doing the elimination we just mentioned. It wouldn't wait for the chlorine to leave and then come in and attack. It can't attack the electrophilic site directly because it's too crowded, because it's tertiary. So because it's unstable though, it would immediately attack or be much more likely to collide and attack at the beta position. Once that rotates anti-periplanar to the leaving group, kick the leaving group out. And so that would give an alkene side product. That would be the major product. So if we want the OH there, we need a weaker nucleophile that will wait. It's not so unstable. It's not going to start picking off protons. It's not a strong base. It will wait. Once the leaving group leaves to produce a carbocation, then it will be able to attack and get deprotonated and leave behind an OH at that position, as we showed. In Chapter 9 last semester, we saw a couple ways to make alcohols. So these reactions gave us some control, regioselective control over which side of an alkene an OH ends up getting connected to. So this was in the chapter we talked about alkenes in addition reactions. So people might want to review that if it's not familiar to you. We said there are two different ways to get a Markovnikov addition across an alkene of an OH and a hydrogen. Right? So we're adding a hydrogen here. There were initially two, now we have three. Right? So we're adding a hydrogen on one side of the alkene and an OH on the other. And that's a hydration reaction. Hydration means we're adding water, the components of water, a hydrogen and an OH across a pi bond. So if we use this dilute sulfuric acid, we may get the same product as these other conditions. So why do we have two different conditions? Well, the dilute sulfuric acid goes through a carbocation intermediate. And what that means is that it could possibly rearrange. So depending on how that first carbocation looks, if it's not the most stable carbocation the molecule could form, and it could rearrange through a hydride or a methyl shift to produce a more stable carbocation, it would do that. And that would give us potentially a different product. So let me get a little bit more space here and show what I mean by that. Right, so let's say we wanted to convert this alkene into an alcohol. And the alcohol we want to make, actually, let's pretend this methyl group is not here. So we've got this alkene, we want to make the alcohol. Let's say we want to make this alcohol right here. I'm going to put the OH group there. So that's a Markovnikov hydration. We have to put an extra hydrogen because we've got two hydrogens here. We need to put another hydrogen on this carbon and an OH on that carbon. So the sulfuric acid will not give us the product we want. It would go through an undesired rearrangement if this is the product we're looking for. Because first this would pick up a proton from the sulfuric acid, and that would give a carbocation. The proton would end up adding to the right carbon, the end carbon, to avoid the unstable primary carbocation. Electrons would come out here and connect that here, leaving this carbon without a complete noble gas configuration. That would be the carbocation. Then, since it's secondary and not as stable as it could be, a hydride shift would occur to make it a more stable carbocation. Tertiary. Then a water would attack there. And so we would end up not getting the correct regiochemical outcome. After deprotonation of the water to the alcohol, we would have an OH at that position. That's not what we wanted. Right, so you have to be careful the difference between these two sets of conditions. The dilute sulfuric acid goes through a carbocation intermediate, as we just showed, and that could potentially rearrange and not give you the OH where you wanted it. So that's why this set of conditions is an alternative. If you want to make sure that you go from this reactant to this product, The oxymercuration demercuration reaction can do that without producing rearrangement product. So just to quickly show that, if we have the same reactant, what would happen here, we're not going to show the whole mechanism, you're not responsible for the whole thing, but the mercury would attract the pi bond at the same time that its lone pair attacks the pi bond. And so that would give a three-membered ring, where the mercury is carrying the majority of the charge. So because it doesn't go through a carbocation, I don't have to worry about the hydride shifting over and moving the charge. I just have to recognize that the mercury will be attracting these electrons, creating a large partial positive here. So water, or other nucleophile if we so choose, could come in here and open that up. It would go to the more substituted site, not because it's, normally it's going to the more substituted site because of the greater quantity of positive attracting it in there, despite the fact that it's a bit more sterically hindered. And so that would give the alcohol at the correct position. There'd still be a mercury there. We would get a water there. After the water attacks that position, then the water would be deprotonated to get the alcohol, and then the mercury would be replaced with a hydrogen using those conditions. So the hydrogen replacing the mercury, the alcohol being deprotonated would give the alcohol that we're trying to make there. That would look like this. So we don't have to worry about the alcohol going to the wrong carbon because we're not going through a carbocation intermediate that could rearrange. And you want to be familiar with the other hydration conditions that are anti-Markovnikov. So review that reaction as well. Let me know if you have any questions about that. All right, so those are the reactions we talked about last semester to make alcohols, and now we're going to look at some new reactions. Some reactions we have not yet seen, except for some people in lab who are already working ahead on lab 2, which is pretty much everybody. But we're going to look at how to make some alcohols through some reduction reaction. So typically you make an alcohol by reducing a carbonyl. A carbonyl is any molecule that has a CO double bond, or this is a carbonyl group. It could have a hydrogen here. It could have a carbon group there. It could have an oxygen, a nitrogen. So on either side of this CO double bond, I'll put X here, could be a halide, could be any one of these things. So carbonyl specifically is a general term. It refers to any functional group that has a CO double bond and then two things bonded there, no matter what they are. So a reduction reaction causes a change in the oxidation state. And then there's a bunch of stuff in the textbook that refers to oxidation numbers and calculating oxidation numbers. I think that you can read that and get a sense for it. It's fairly well explained. It's probably not very likely I'm going to ask you about oxidation numbers, but I may. So even though I'm going to kind of breeze through this section right here during lecture, you should definitely look at the bullet points on the study guide that relate to these topics of oxidation numbers, and then talk to me sometime in lab or set up a time to meet with me to go over them if you're not sure what questions related to those bullet points might look like on exams, because you may have one. But more often than not, I ask questions about these reactions rather than the oxidation numbers that are used to calculate the reaction. So I'm just going to kind of skip through this section on oxidation numbers and start to talk about the reaction. So this is the net consequence of these reduction reactions. It typically converts the carbonyl group into an alcohol. So what's necessary to do that? From a reagent standpoint, what's the difference between these two structures? Well, one thing I notice immediately is the oxygen is now an OH. So I need to provide a hydrogen. Obviously, that oxygen is going to pick up a hydrogen. So it might be your instinct to say, well, maybe HCl would work. Well, this oxygen has a couple lone pairs. It's got a nice, decent partial negative. HCl is a really strong acid. So I could imagine the oxygen picking up a proton from the HCl, and that would happen if I add HCl to a carbonyl. The carbonyl would become protonated. That would create a positive. I could imagine these electrons swinging out here, and that would create this structure here. The problem is when these swing out, it creates a carbocation. So to get from the carbonyl to the carbocation, which would actually be in resonance, sharing the positive between both the oxygen and the carbon, that's what would happen if I use HCl. But if I want to reduce it all the way down to the alcohol, I'm not just adding the hydrogen that you see to the oxygen, you also have to add a hydrogen to this carbon. Right? There's no hydrogen on this carbonyl to begin with. Now there is one. So when a reduction of a carbonyl occurs, there's always going to be a hydrogen that's going to be added to the carbonyl carbon to go from 3 sigma bonds and a pi bond to 4 sigma bonds. And so that's the key. Not only do we have to add the hydrogen in there, we also have to add the electrons. Those electrons are not already there. There's no electrons there. So we're going to add a reducing agent to cause this reduction. The reducing agent itself is going to be oxidized because the reducing agent isn't itself reduced. It's providing the elements to reduce the carbonyl. And what elements do we need? We need a hydrogen and we need a pair of electrons. And a hydrogen with a pair of electrons is called hydride. So that's why most of these reducing agents are going to, if it's going to be reduced specifically by adding a hydrogen in there, it's going to have to be a hydride that we need. So no, HCl is not going to do it. HCl cannot deliver a hydride. It delivers a proton and the electrons stay behind. So that could be useful at the end to provide this proton as we saw in this form here. But what we need is to deliver a hydride to the carbonyl carbon. That's the key to the actual reduction. And so we need something that involves a hydrogen where the hydrogen keeps the electrons and then uses them to attack and delivers them and uses them to make a new sigma bond there. So one way to do that would be add H2. H2 consists of a hydrogen with electrons and a proton. So I mean, you can think of them as being shared evenly, but if the hydrogen with its electrons comes in here, and these electrons shift up, and then those electrons pick up the proton, that would also give the product. And that reaction works. The problem with that, though, is the kinetics. We saw last semester how if you want to convert an alkene, a carbon-carbon double bond, something like this, into an alkane, that's also a reduction, that works well with any one of these catalysts. I can add the 2 hydrogens across the pi bond. They would end up adding to the same side since it's a syn addition. But if we compare an alkene with a carbonyl, which is what we're talking about now, and we look at the kinetics involved, the alkene is not nearly as stable as the carbonyl. CO double bonds are more stable than CC double bonds when you look at the bond energies involved. So for the alkene to get through this reaction with the aid of the catalyst, it's a multi-step reaction, but we're just going to look at the first part, which would be the slow step. To get through the slow step and then, through the rest of the reaction, there's only so much activation energy because the alkene already starts high in energy. So most of the collisions may have the energy necessary. And the alkene will readily undergo hydrogenation. For the carbonyl, though, because it's more stable with the CO double bond, to get up to that same level of instability when the hydrogens start to add across that pi bond, it takes a significantly higher activation energy. So it's a slower process. So to facilitate that process, I usually need a high temperature, so the collisions are strong enough to make it up there, and I need a high pressure, meaning pressure of the H2 gas. So you have to have a container, you can pump with H2 gas to a pretty high pressure, and you have to really pack that H2 gas in there to facilitate all the collisions that are necessary to make this product. So that may work, but if the high temperature starts to break apart the molecule, or the high pressure these are forceful conditions, it might end up adding the hydrogens across, but it might start also breaking up the molecule and causing other side reactions, right? If there's enough energy to undergo this reaction, there may be enough energy to undergo some other side reactions that you don't want to occur. So this is not the ideal way to reduce a carbonyl compound. You can use it though, so you want to be aware of its limitations kinetically, but the fact that it could potentially be used if you have the right material. You need a special reaction vessel though that you can pump in, to like 10 or even 100 times more pressure than normally exists in the atmosphere. So that wouldn't work for us in our lab without those vessels. So an easier way to do this reduction reaction is to use a hydride compound. So the sodium borohydride looks like this. Boron has a negative, and for boron, that's really pretty unstable. Boron's a very small atom. It only has 5 protons, so that extra negative means it has the equivalent of 6 electrons, so that's a charge ratio. It's not very balanced, so it's pretty unstable. So it will readily give up the hydrogen and the electrons to avoid that negative charge. So as these two molecules collide, this hydrogen pulls the electrons away from the boron. It's slightly more electronegative than boron anyway. And so it'll pull the electrons in and use them to form this new bond and push electrons up to the oxygen. And then the solvent is going to be protic. Whatever solvent you choose, it's going to have a proton that this oxygen can pick off, and that gives you the alcohol. So you can make a ketone into a secondary alcohol in a decent yield using these two reagents combined. The nice thing about this is it happens in one step. We don't have to worry about the hydride picking up a proton directly and producing hydrogen gas because the NABH4 is not extremely reactive. It's more selective, so it really pretty much will only deliver the hydride to the carbonyl carbon. So that's one option. Another option is lithium aluminum hydride, which is abbreviated LAH. The molecule involves a lithium as a spectator counterion, and then there's aluminum that will be bonded to 4 hydrogens. So this is lithium aluminum hydride, or LAH. And this is similar, but aluminum compared to boron is significantly less electronegative. I should have looked this up. I don't know the electronegativity of aluminum offhand. I know it's definitely below 2, so the hydrogen versus the aluminum is an even bigger electronegativity difference here, a large partial negative. The aluminum needs to get rid of these hydrogens to make its noble gas configuration. So these hydrogens are even more strongly, much more strongly pulling electrons away from the aluminum than they were pulling electrons away from the boron. So this is very reactive. It will react with pretty much any carbonyl and push these electrons up here. And so that will temporarily create a negative there. This hydrogen is now there. So there was already 1 hydrogen there. Now there are 2. And in this case, the water has to be added in a second step. That's really important. So if you're doing this reaction, you can't write LAH and water. That implies that they're added together, which will not work. If water is around near the LAH, then the LAH will just pick up a proton from the water. producing OH minus and hydrogen gas. So that's why we have to wait. So we're not going to have any water in there. We're only going to add these two together. The LAH will collide there, push electrons up, and all the molecules will be converted into this negative because, oh, I left that negative out, sorry about that. The oxygen is better at stabilizing a negative than aluminum. So this first step is pretty much irreversible. The oxygen's not going to be able to swing back in and push out a hydrogen with electrons. That's a terrible leaving group. It's not going to be able to leave. And so all the molecules effectively get converted into this intermediate, and they hang out like that. You can do that overnight. You can wait 3 or 4 days. They'll all just sit there and wait until water is added. And when it is added, it will allow a proton to be donated to make the product. So that's the LAH reaction. And so what are the differences between these two reagents? This one is weaker. It's less reactive. So if you want to try it and it doesn't work, you can try the stronger LAH. It's more reactive. The downside is you can't allow any water in. You have to wait till the second step to add the water, just like we did for those of you who set up that Grignard reaction for lab 2. You had to flame dry the flask and then put it under a nitrogen atmosphere to avoid water. We'd have to do the same thing here because we don't want the hydride reacting with the water. We want it delivered to the carbonyl. So this slide does a nice job of contrasting the 3 reagents we just talked about for reduction. If you want to just reduce the alkene, you can also do that. So if you want to keep the CO double bond intact and you want to add H2 across the pi bond, the CC pi bond, you can do that. And if I were giving you a question like this on the exam, if you just put hydrogen, platinum, palladium, or nickel, any one of these 3 catalysts with the hydrogen and drew the product, I'd give you credit. If you expect the hydrogen to add across the CO double bond pi bond to make the alcohol, then I would expect you to put pressure and temperature, or at least one of those two at least, to indicate the hydrogen is not strong enough to react across both these pi bonds. The alkene's already higher in energy, so it doesn't require much activation energy for it to react there and hydrogenate the alkene. But if you want the hydrogen to add across the CO double bond, you need higher temperature and more collisions for that to occur in a reasonable time frame to reduce that to the OH. So it's possible, but you just want to be more specific about the conditions you'd use if you're hydrogenating both versus if you're just hydrogenating the alkene. What's also nice in terms of selectivity is neither of these hydride reagents will react with the alkene. So we can selectively react the alkene if we want. We could react both, or we could selectively react just the carbonyl by delivering a hydride there from either of these hydride reagents and converting that into alcohol while retaining the alkene function group at the other position. There's also a lot of customizability, and we'll talk more about this later in the semester. For now, we're not going to get into much detail on it. In terms of converting LAH into this and other versions where we might put R groups here or cyano groups or specifically sterically hindering R groups here, that alters the reactivity of this hydride, and we can do the same thing with the boron. And we'll see some examples where different things attached for these R groups will affect the reactivity, and it will give us a selectivity. So that's really not anything we're going to get into detail on now, so you don't have to worry about that too much. But I just wanted to point that out because these reagents, especially the LAH, is very harsh. It'll react in any carbonyl carbon. But if you make it less reactive by putting steric hindrance around it, you can control its reactivity a little bit more. So there's a lot of options there. Other types of functional groups, carbonyls can also react with LEH. So as you said, LEH will react with almost any CO double bond functional group. So what we saw so far was if you have a ketone and you use LEH followed by water, you convert the ketone into an alcohol. If you had an aldehyde is basically the same as a ketone, except for on one side we have a hydrogen, and use LEH and water in a second step, you'd make a primary alcohol. Draw that again. So we can make a secondary alcohol or a primary alcohol starting from those two. There are other carbonyl compounds that it will also react with. So any CO double bond should be susceptible to reacting with the hydride of the lithium aluminum hydride. And so as we were saying, the hydride would come in here, push these electrons up. Here though, we have a protic site. So really the hydride would pick up that proton first. Then a second hydride would come in here and push that up. And then some more stuff will happen that is more relevant in chapter 21 that you don't have to worry about yet. But eventually that will convert the carboxylic acid to a primary alcohol. So I probably won't ask you about that until later when we get into chapter 21. This reaction, though, you definitely want to be familiar with. So if I want to convert an ester into a primary alcohol, LEH is a very effective way of doing that. So let's talk about that mechanism. So here's an ester. An ester consists of a carbon group bonded to a CO double bond, and then an oxygen, and then that oxygen is bonded to another carbon group. It doesn't have to be a methyl, it could be any R group here. But what will happen here is I'll have multiple units of hydride that need to react. So the first hydride will collide there and push electrons up to make a negative. And then when that negative swings back down in, this is a decent leaving group. It's not a good leaving group. And we've seen an oxygen with a negative is actually a poor leaving group. But we've already got an oxygen with a negative. And we've got an aluminum with a negative that's even more unstable. So this first step is definitely not reversible, because the negative on the oxygen is more stable than a negative on aluminum. Oxygen has a higher electronegativity and better ability to attract electrons and carry a negative than an aluminum. So this first step is irreversible. The next step, when these electrons swing in and push that out, it's going to form this. So which negative is more stable, this one or this one? Well, they're pretty similar. You could imagine this oxygen coming back in, pushing electrons up. So that one might be reversible. But from what we said earlier today, if I have a negative on this large structure that's got anything crowding nearby, it's going to be hard for solvent to come in and stabilize it, versus on a methyl group, which is much smaller, there's going to be lots of solvation to stabilize that. So it's going to be product favored. And this step also is favored by entropy, because I'm going from one molecule breaking it into two. So that step is definitely significantly product favored, despite the negative existing on an oxygen and continuing to exist on oxygen. So this substance would just basically float around in solution for a little while. And then the aldehyde that's created, which is right here, would then still be susceptible to reacting with another hydride from another molecule of LAH. That's why we need two molecules of H minus from LAH to come in there. And the second one would push electrons up. And then this is basically stuck. It can't do anything else. So this step is also pretty much irreversible, because the negative on the oxygen is way more stable than the aluminum. And so that all is going to be step one, right? Remember, we said this has to happen in two steps. Step one, we add the LAH. That carries us through. This is all part of step one. There's different steps of the mechanism, but this is all part of part one that occurs specifically after adding the LAH, the lithium aluminum hydride. So that's part of it. This is part of it. This is part of it. And then this is step two. So at the end, this is like accumulating in solution along with the other negatively charged oxygens. And then by adding the water, we provide the proton source to pronate those sites. So we would also get a methanol, which would be easy to remove through evaporation. Depending on our choice, we may also even add some acid here just to make sure that this last step really is product favored, right? Because if this water donates a proton and produces OH minus, well, that might start picking these protons back up to some degree, which would shift the equilibrium back. So adding an HCl or something would just pronate all those sites and shift that really pretty much exclusively toward the desired product. If we're trying to make an alcohol, that's one way to do it. All right, so here's another example. Let's take a look at the reactions we just learned and apply them. So one thing about the NaBH4 with water is it's more selective. It's a weaker hydride delivering agent. It's more selective. I don't have enough space to draw the product there, so I'm going to draw it down here. But the NaBH4 won't react with the alkene. It won't react with the ester. It will only react with aldehydes and ketones. That's what we have here. We have a ketone. So I expect the hydride to be delivered there, push electrons up, and then that oxygen to get protonated by water. And so that would produce an OH there. This functional group would remain unaffected, and so would the alkene. Then if I react that with LAH, the LAH is going to reduce the ester. And through the mechanism we just saw, the hydride would come in, push electrons up. When they swing back down, it will push that oxygen leaving group out. So that breaks open the ring. Then another hydride would come in, push electrons up onto that oxygen. The hydride will also deprotonate that site. So we need lots of extra equivalents of it to deprotonate there and react twice at the carbonyl carbon. But then once I add the H3O plus, it's going to provide the proton for that OH to reform. So I'd still have an alcohol there. This ring, as we said, is going to open up right there. So let's number these so we can keep track of them. So I've got 9 carbons and oxygen there, number 8. So 1, 2, 3, 4, 5. Carbon 5 and 6 is an alkene. That's not affected by LAH. Only carbonyls have the polarity to attract the hydride in. So that'd be 6. This is still a cis double bond or an E configuration. So that'll be 7 and 8 will be an OH. So, oops, that's carbon 7 and the oxygen is number 8. And then what's happening here is carbon 4 still has a carbon 10 bonded to it, and then carbon 9, and the carbon 9 would also have an OH. Because the hydride would come in, push those electrons up, they'd swing back down, then this oxygen 8 would be a leaving group, and it would later be protonated after H3O plus is added. But then a second H would be delivered, so that's why there are 2 new hydrogens on carbon 9. There weren't any there initially. 2 new hydrogens come in from 2 different H minuses delivered by the LAH, pushing the electrons up to create a negatively charged oxygen, which is then protonated in the end by the H3O plus. In terms of the stereochemistry, this chiral center here was never told to us whether it was a solid dash or a solid wedge or a dash wedge. So let's just assume maybe it was dash to begin with. That would remain so. That wouldn't change because there's no reaction occurring at carbon 4. Carbon 2, though, is achiral to begin with and becomes chiral. So I would want to show that. I could show that with the zigzag. The zigzag there would indicate that half the molecules have a solid wedge at that position and the other half have a dashed wedge. So you want to make sure that you communicate about the stereochemical outcome for these reactions. All right, so that leads us to the second quiz question. Applying these three new reactions. So we know NABH4 is not very reactive. It won't do anything to the ester, but it will reduce a ketone. It also won't react with the alkene. So the only thing reacting here with NABH4 should be the ketone. So that would mean that everything else remains intact. Except this ketone becomes an alcohol. And since it's flat now and the hydride could be delivered from the top or from the bottom, it could push the OH forward or back. So half the molecules would have a dashed wedge there and half would have a solid wedge. So the zigzag communicates that. The LAH is more reactive. It will react with both of the carbonyl carbons. So it would do the same thing that the NABH4 does here, but also react the ester. And that would push this out as a leaving group, which means two hydrogens are going to be delivered to this site. And when that leaves, it's going to also be protonated in the end by water. So the leaving group is going to be there as an alcohol. And the rest of the structure, again, the LAH does not react the alkene, but it will react the carbonyl and convert that into an OH. That does not create a chiral center. And it will also deliver hydride here, pushing electrons up there. And as we said, that could happen from the top or the bottom, so that does create a chiral center. And so that would be a good way to show that structure. This would probably easily evaporate out, so we're probably not going to worry about that moving forward. And then if this structure were to react with hydrogen, the hydrogen would react with the alkene, adding two hydrogens across the alkene to make that into an alkane. So the product there, the OH groups would not be affected by that hydrogen, but the alkene would be converted to an alkane. So you definitely want to do some practice with those reactions. Let me know if you need help with any of that practice. All right, so that's alcohols. Some molecules have two alcohols. We just worked with an example of a diol. Two alcohols on the same structure, di meaning two, all meaning alcohol. So there are a variety of different diols. Lots of different molecules have more than one OH group attached. Those are called diols. You could also have a structure that had an OH group here, and maybe one here, and then maybe one here. What would that be? Well, that would be a triol. All right, so just to name that one, I'd find the longest chain, be 5, so it'd be pent. I have an OH on carbon 1, 3, and 5. So it'd be 1, 3, 5, pentatriol. So instead of pentanol, actually, I think I need an N here. Pentane. Pentanol, it would be pentane triol. Yeah, actually, there might need to be an E here as well. The spelling isn't as important as to making sure you have the right prefixes and suffixes where necessary. So the tri meaning there are 3 alcohols, the ol suffix meaning there are specifically alcohols that we have 3 of, and then the pentane meaning we don't have any alkenes, but there are 5 carbons in the parent, and then we do need the numbers to tell which carbons the alcohols are connected to. So one way to make a diol is to start with a dicarbonyl. A molecule with 2 carbonyl sites. You just need double the equivalence of the reducing agents. This one would require heat and probably some pressure, but any one of those 3 could potentially reduce both ketone sites to alcohol through the mechanisms we just saw. From last semester, you may recall in Chapter 9 we talked about alkenes. There's two ways to make a 1,2 diol. So the specific type of diol here is a 1,2 diol because the two alcohols are on carbons 1 and 2 with respect to one another. And if you recall these sets of conditions, well, determine whether I get the alcohols on opposite sides spatially or on the same side spatially. So you want to be aware of what the osmium tetraoxide does to add two OH groups on the same side of the pi bond, both with solid wedges or both with dashed wedges, versus the peroxy acid, which if you use that, you will first convert the alkene into a epoxide, and then the H3O plus protonates that, makes it an extremely good leaving group, and that would always be with water. The water would then attack that, open it up, and since one side is blocked, it would have to attack from the other side. And so that would initially give, nothing's happening here, so that OH group's still connected there with the solid wedge, just like it was initially. But when this comes in, it has to come in from the other side. Right, so this is the water. It has to attack from behind if the front is blocked by the epoxide three-membered ring. And then that would be deprotonated, and that's why I get the OH groups on opposite spatial arrangements when I use this set of condition. So make sure you review those reactions as necessary. And then there's going to be one more reaction we're going to talk about today, and that's the Grignard reaction. So many of you are already familiar with this from Lab 2 that we've already had a chance to get started with. But the Grignard reaction is a classic example of an organometallic reagent. So organometallic means there's a carbon organic compound that contains carbon connected to a metal. And what organometallic reagents have in common typically is that the metal is less electronegative than carbon. Carbon's not a very high electronegativity atom. Right? Normally, most things like halogens, oxygen, nitrogen, the most common things that bond to carbon, other than hydrogen of course, are more electronegative than carbon and pull electrons away from it, creating a positive on the carbon that makes it electrophilic. So some nucleophile maybe attacks it and pushes out the leaving group. So we've seen a lot of examples where carbon has things attacking it. But in an organometallic reagent, like a Grignard reagent, the carbon is attracting electrons away from the metal. And so it takes on a very nice negative. And that makes it itself a good nucleophile. And so that's what we're going to see with the Grignard reagent. So before we can talk about what the Grignard reagent does, we want to talk about the formation of the Grignard reagent. So this involves using metallic magnesium, and the magnesium has a couple extra electrons it needs to get rid of to make its noble gas configuration. So it's going to come in here and deliver those electrons to the carbon and use them to form a new sigma bond. And that sigma bond shifts mostly toward the carbon. And the magnesium really would prefer to be without those electrons completely. What's nice about this is it's a rare example where we see electrons able to come into an aromatic ring. Normally an sp2 site, a nucleophile can't really attack that, but we have an example of that here. If the magnesium comes in with a pair of electrons and forms a bond there, or if it comes in with its electrons here, which makes more sense since it's the primary site, either way, it's going to make a new bond, and that's going to reverse the quantity or type of charge that's on that carbon. Normally a carbon with a halogen attached has a partial positive. Now it's got a partial negative. Here this carbon has a partial positive. Now it's got a partial negative. and that makes it nucleophilic. Because if the magnesium wants to make its noble gas configuration, it needs 0 electrons in its valence shell. It needs a +2. So it's almost as if the carbon here has this lone pair that the magnesium is attracting to. It's almost like an ionic attraction, but there is some degree of sharing. So you may see a Grignard drawn in both of these ways. You may see the Grignard written with a lone pair and a negative on a carbon, which clearly is a great nucleophile, very unstable, very reactive. Or you may see it with a partial negative or even no charge shown and just sharing electrons. You want to think about it as both of those kind of simultaneously, which may not seem intuitively reasonable, but the reality is it's somewhere in between those two states. It's not fully sharing, it's not fully ionic, but it is a great nucleophile. So again, here's another example where we're talking about that. The electronegativity difference here is a pretty big difference. Difference between the carbon and the magnesium creates a very polar bond. So whether we think of carbon as having a large partial negative or a formal negative with a lone pair, either way, it can use those electrons to attack a carbon and form a new bond. And so that's the key. It's a great nucleophile. It's also a great base, though, and that's the downside. So when we did this reaction with phenyl magnesium bromide in lab, we had to flame dry, we had to put it under a nitrogen atmosphere so there wouldn't be any water, because if there's water around, then the lone pair would just end up picking a proton off of water. But that's not what we want. I mean, it's easy, if we have that, we're just converting it into benzene, which is easy to buy anyway. So the idea here is, whatever that R group is, sharing electrons with magnesium, it's going to take the electrons away from the magnesium, so the magnesium can make a noble gas configuration with the 2+, and it's going to use them to connect to a carbon. And if that molecule we react with is a carbonyl, like we did in lab, it'll push electrons up to make a negative, and then later in a second step, a water or an acid would be added, and that would protonate the oxygen to make an alcohol. So this is another way of making an alcohol. The advantage here is at the same time we make an alcohol functional group, we've added a new carbon-carbon bond. And we can control where that bond is formed by making sure there's only one electrophilic site that nucleophilic Grignard reagent will attack. As we said, it's very reactive. So if there's any moisture, it'll quickly react with water, and that will be virtually irreversible because there's a massive pKa difference there that shifts pretty much exclusively to the product side. So we can't use water while the Grignard is reacting, right? We're only going to use water in a second step after we've given plenty of opportunity for all these collisions to occur and for all of the carbonyl compounds to be converted into alkoxides. So if we can't use water because it will react directly with the Grignard, what solvent is appropriate? The best solvent for a Grignard is an ether. So you'll usually see the word ether, or you might see the structure of an ether, and diethyl ether and THF are the most common ethers. The Grignard reagent we bought for you to use in lab 2 comes in THF as the solvent. What's nice about THF is it's polar enough, and especially with the partial negative there, to attract to the magnesium. So it helps the magnesium leave and form a nice attraction to this oxygen and leave the carbon to be more of a naked nucleophile so it can attack the electrophile more readily. And it's also aprotic, that's the key. It doesn't have a proton that could be picked off readily, so we don't have to worry about this lone pair picking up a proton off the solvent like we would if there was any water or any other protic solvent around. And the answer here is flame dry under vacuum and use a nitrogen atmosphere to prevent air and moisture from interfering with the Grignard. So a couple more Grignard examples. So if I have a malpho group sharing electrons with magnesium, the magnesium will leave those electrons and it'll come in here and push electrons up. Then that oxygen will be protonated, and I'll be able to make what was a secondary carbon into a tertiary one. So I can make a tertiary alcohol. If you're looking to make a tertiary alcohol, Grignard is a great way to do it. If the tertiary alcohol you want to make has two identical carbon groups, then you can start with an ester. So this is very similar to the LEH reaction with an ester. What would happen first is the magnesium would leave these electrons on the carbon. They would come in here, push a pair of electrons up. That would make a negative on this oxygen. The extra CH3 group is now installed. So what happened next is this would swing in and push out this not great leaving group, but more stable with the negative on an oxygen than on a carbon. So that would continue. That would make a ketone, and this OMe would be hanging out with a negative, waiting for this water to be added later on. But now it's susceptible to another Grignard. So as long as I have excess, another molecule will pull the electrons away from the magnesium and attack there and push electrons up. So that's how I can install two identical groups. The first one attacks initially, and then after the leaving group leaves, another identical methyl group can attack, and I'll end up with two methyl groups there. So that's a key thing. If you're trying to synthesize a molecule with two identical R groups, you can install both of them from two subsequent attacks of a Grignard, identical Grignard reagent. So what are some functional groups that are not compatible with the Grignard? Well, alcohol, amines, water, carboxylic acids, really anything that's protic. As we said, the Grignard reagent is designed to attack a carbon and make a new carbon-carbon bond. But if there's anything that's protic, any kind of structure that has a proton that could be picked off, the Grignard will also pick up that proton. If the negative on whatever X is, if the negative on it can be fairly well stabilized, that proton is a goner. And the Grignard is a goner because once it picks it up, it no longer has a lone pair to attack. So you can't use anything that's protic. All right, so let's look at these. So let's see if we can make these structures using a Grignard reaction. And what that means is we can make pretty complicated structures with lots of carbons by only starting with much smaller molecules that maybe only have a few carbons. So that's the idea here. So let's count these carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I want to make this molecule in one step for molecules that each have 5 carbons or less, my disconnection is going to be right here. I've got 5 carbons in one piece and 5 carbons in another. I just have to figure out how to make that bond between 3 and 6. And the Grignard will allow me to do that. So if I keep the oxygen on carbon 3, that could be my carbonyl. 2, 3, 4, 5. And then carbon 6, I need it to connect to carbon 3, so I'll make that my Grignard. Six, 7, 8, 9, 10. So the magnesium is sharing electrons with carbon 6, but not very effectively. So basically, those electrons would exist on 6 as a lone pair, and so those would come into 3 and push these electrons up. That'll be step 1. And then the second step, I would use water, right? So the attack, pushing electrons out and make that oxygen negative, and the water, and maybe some H3O plus, would pronate that oxygen to make it an alcohol. And so I can build up a pretty complex structure by making this new carbon-carbon bond. So you can see the power of starting with simple small molecules that you can buy and then quickly building up a more complicated structure through these reactions that allow you to form new carbon-carbon bonds. If we want to do the same type of thing down here, we count these carbons. So here I only have 9 total, 5 and 4. So this one could be done in a couple different ways. Probably though, since this OH group is connected here, I want to start off with a CO double bond at that site. So what you'll notice is whichever carbon becomes an OH or has an OH, ends up with an OH attached to it, that would have started with a CO double bond because the remaining carbons could then be thought of as the Grignard reagent. So whether I show those electrons shared or as a lone pair, it's going to be a big partial negative there, and that's going to cause them to attack and push electrons out. So I'm forming a bond between 1 and 5 by making one of those sides electrophilic and the other side nucleophilic, and allowing the partial positive and partial negative to attract and share that pair of electrons in to make the new bond. I'll push these electrons out to avoid 5-bonded carbon for sure. We don't want to draw any 5-bonded carbons. And then that negatively charged oxygen would require a second step where H3O plus and water pronated. All right. So let's say I wanted to make this structure. Well, that's a bit tricky. If I'm thinking about adding onto my structure, I can imagine trying to make this new bond just like we did in the last example. That would require me to start off with this chunk. And instead of having a COH, I'd have a CO double bond. And then the other chunk, I could imagine, let's number these. I can imagine carbon 1 here as a Grignard coming in and attacking and pushing electrons out to make the new bond there. Problem is, as we said a minute ago, you can't have any product functional groups around in the presence of a Grignard, because if you do, then the Grignard will reach around and pick off that proton. Or another molecule of the Grignard would use its lone pair to pick off that proton. So you can't have any product sites on any of your structures with the Grignard, or the Grignard will just pick up a proton. So one strategy synthetically to make this molecule through a Grignard reaction and overcome that limitation is to use a protecting group. We protect the alcohol by converting it temporarily into another non-product group that the Grignard won't react with, and then later we remove that protecting group to restore it to its correct shape or structure. So if this is a molecule I want to make, I can think about disconnecting and making these structures, but since I can't make a Grignard and an OH on the same molecule because they'll react together through a proton transfer, the general strategy is to use a protective group or protecting group. So I convert the OH into something that's aprotic. I get rid of that proton and put something else on there that the Grignard won't react with. Then I add magnesium to make the Grignard. Then I add the carbonyl. So this would be step 1, protect. Step 2, add the magnesium in this ether solvent to convert that into the Grignard. Step 3, add the carbonyl that the Grignard is going to then react with. Step 4, I'd add H3O plus and water to provide that proton. And then step 5 would be deprotect. So the whole deprotection part, or the whole protecting group deprotecting, those 2 steps combined add 2 extra steps to the overall process. but at least it makes it possible, because without those two steps, as we showed, the Grignard would just react with itself and nothing, no product would form at all. So one protecting group, just to quickly mention, an example is this TMS, or trimethylsiloether group. So the alcohol, whatever it is, would be converted to an OTMS. And that just, basically what's happening here is the alcohol comes in here and pushes out the chlorine. And then this acts as a weak base to deprotonate the alcohol. So instead of an OH, this picks off the H, and I end up with an OSI. And so the oxygen has a bond to a silicon, and that won't react with the Grignard. So that would be step one. Then in step two, I'd use magnesium and ether, and that would allow the magnesium to insert there between the bromine and the carbon. Now it's got this nucleophilic site that I want. I can have that attack the carbonyl, and then later I can deprotect it, right? But the point is, since it's no longer an OH, I don't have to worry about the Grignard reaching around and reacting anywhere over here on this protecting group. In other words, the alcohol isn't an alcohol anymore. I've converted it into something else, but it's basically a protected alcohol because it can't react, but it can be restored to its alcohol form whenever I want. Just to point out, you may be wondering, well, how can this attack here push out a leaving group if it's a tertiary site? Well, it's a tertiary silicon atom, and it is kind of blocked, but the silicon atom is not nearly as blocked as a carbon. So if this silicon were a carbon, this wouldn't work. You can't have a nucleophile attack a tertiary carbon and push out a leaving group in one step because it's too crowded, right? A carbon, it's too crowded if I've got methyl groups or other R groups for anything to come in there. But a silicon is a much larger atom, right? Carbon's got 2 energy levels, silicon has 3. So as a larger atom, even with those methyl groups, there's still space here for a nucleophile to attack. So if that oxygen from the alcohol sneaks its way in there, it can connect to the silicon and push the chlorine out the other side, which is exactly the reaction we just talked about. So I'll come back and talk about TBAF in a minute. All right, so here's what's happening. This comes into the silicon, pushes out the chlorine, the nitrogen deprotonates the proton there. That installs the protecting group. I use the magnesium to make this into a Grignard. The Grignard attacks the carbonyl in the next step, pushes electrons up. And then there's a 3 missing here. We need some H3O plus and water. That would protonate this oxygen. And then I'm almost to the final product that I actually wanted to make. I just have to remove the protecting group. So how do we remove this specific protecting group? We use fluoride ions. Fluoride ions are difficult to work with because they react with glass. So I definitely have to use a plastic container instead of glass. But the idea is there that the fluoride, let me redraw this molecule here so we can see what the fluoride would do. So the TMS looks like this. There's a silicon with 3 methyl groups. So the fluoride from the TBAF, which to me is like a cool sounding thing, the fluoride forms an even stronger bond with silicon than oxygen. Silicon-oxygen bonds are strong, right? That's what's in glass. That's why it's hard to etch glass. You can't really scratch it. Its surface is strong because the silicon-oxygen bonds are quite strong. But fluorine makes an even stronger bond. That's why fluorine etches glass. If you have, fluoride, the fluoride ions attract even more strongly with silicon, and it breaks the silicon-oxygen bonds. So that releases that oxygen, and then the oxygen would pick up a proton from H3O plus or whatever solvents around, and it would become an OH. And so that's the deprotection step. The fluoride reacts with the silicon and pops off the oxygen so that it can be protonated and give the final product. So there's a lot of synthetic organic chemistry that involves putting a protecting group on, doing some reaction that wouldn't otherwise work, and then removing the protecting group. So if I ask you about protecting groups, I may give you an example where this specific protecting group is used, so you want to be familiar with it and the reactions we just talked about involving it. Or I may give you more of a conceptual question where I say something like, describe how protecting groups work in detail. So you would want to be able to recognize that if you have a functional group like an alcohol that would otherwise interfere with the Grignard reaction, converting the alcohol temporarily into some other less reactive group, then doing the reaction you want, and then removing that and restoring the alcohol to its original form is the basics of that strategy. All right, so that gets through a large chunk of chapter 13 we needed to cover. There are a lot of bullet points related to that, so just to remind everyone, Tuesdays, which is tomorrow, in the evening, there's only one student in the Tuesday lab. So that student will be taking their exam at 5:30 or shortly after if they have any questions requiring last minute review. So probably around 6:30 if you want to come into lab and review any of these bullet points or other practice examples, you're welcome to do that as long as there aren't too many people. So far, one person has contacted me about coming in tomorrow, which means we still have space for more people. But if you want to come in on Tuesday, each week you'll have to message me because obviously we can't pack the lab with too many students. It's unlikely that demand will exceed the limit of the space that we have there in the lab, but just to be sure it doesn't, just send me a message and let me know if you're planning to come in Tuesdays each week, if you plan to come in around 6:30 to review anything. But that's a good opportunity since most of you have labs on Thursday. Coming in on Tuesday evening would help you prepare. If you have lab on Tuesday afternoon and you want to review with me over the weekend or on a Monday after class or something, let me know. We could always talk about some of these bullet points or go through some of the examples here or other examples that you may have questions about. So definitely practice these up for the reactions we talked about today. And then on Wednesday, we're going to continue with the rest of chapter 13. And we're going to talk about some other reactions that alcohols undergo. So far we talked about how to make alcohols. And then on Wednesday, we're going to talk about some of the reactions that alcohols will undergo themselves to convert alcohols into other functional groups. And we're going to introduce some more reactions beyond what we saw last semester. So to prepare for that, you want to check out these videos, read the sections, and try to answer the day 6 quiz questions, obviously before 1 p.m. on Wednesday. All right, so feel free to stick around if you do have any questions about anything. Go ahead and unmute yourself.